Okay, so let's start with first problem. A certain volume of ideal gas doubles its volume under isothermal conditions. What is the gain in internal energy and what is the gain in entropy of the gas? So what is the change in internal energy and what is the change in entropy of the gas? That's a question. So let's analyze the data given. So it's a problem involving ideal gas, one of the second category of problem that we have discussed. So a certain volume of ideal gas is given. Okay, it doubles its volume. So I can say that the final volume V2 is equal to twice the initial volume. So this is one data that is given under isothermal condition. So you can say that T is equal to constant. Yeah. What is the gain in internal energy? Yeah. So let's attend part A first. Gain in internal energy. So hope you remember the internal energy for an ideal gas. Internal energy of an ideal gas, hope you remember, U is a function of temperature alone. That is for an ideal gas. This is the concept that we have discussed and learned in the previous modules. U is a function of temperature alone for an ideal gas, or the internal energy of an ideal gas system is independent of the volume, or it's independent of the pressure. And we concluded that see something like dou U by, is it not, dou U by dou V, change in internal energy with respect to volume at constant temperature, is equal to dou U by dou P at constant temperature. Both of these quantities for an ideal gas system is equal to 0. Okay, so that gives you the answer for the first thing. What is the gain in internal energy for the ideal gas system when doubling the volume? There is no gain. Okay, so I can say therefore in this case du is equal to 0. That is a conceptual question that we have to answer. There is no change in the internal energy of the system, but you will see that even though there is no change in the internal energy of the system, we will see that there will be a change in the entropy of the system. So let's calculate, and that is a straightforward equation for us, right? So it's ideal gas system under isothermal condition. So we have ready-made equations for us. So what is that? Delta S for isothermal process. We had a pair of equation for each of the three processes. So what is that? That is nr log. Oh, remember that we had two equations: nr log V2 by V1. V2 by V1, and it was also equal to minus nr log P2 by P1. But here what we are given is V1 and V2. So this equation is enough. So it's equal to are we given the, something about the number of moles here? No, it's not. No data is available regarding how many moles. So let's keep that n as constant for n moles of the gas. Let's complete the problem. So it will be equal to nr log natural logarithm of what is V2 by V1. So you can see from this data V2 by V1 is equal to 2. So nr log 2. Okay. So what you can do, that you can just substitute n into r is 8.314 in SI units. Okay, 8.314 into log 2 which you can calculate, and you will be getting the answer here as some 5.76 n. There will be n. Okay, so if it is for 1 mole, it will be 5.76 joule per kilogram. Sorry, joule per Kelvin. It's not. It's entropy change. So the unit is joule per Kelvin, right? So that is the answer here. So that is a significant thing. Even though there is no any change in internal energy of the system, there will be a change in the entropy. There is a gain in entropy of the gas, because the reason is that the gas has doubled its volume. Okay, the gas has doubled its volume. A complete explanation of this particular process. Okay, see that the gas has doubled its volume, and we have seen that entropy is an extensive parameter, and we will learn in statistical mechanics that S is equal to, already I have mentioned this one, K log omega or K log, this is just a hint, W, okay, and this W is the number of microstates. You will see that this number of microstates will depend upon the volume, even though it is the temperature remains constant. That is yet another reason. Or the disorder of the system would have got increased. Why? In terms of molecular disorder, okay, or thermal disorder, because earlier it was confined to very lesser space where it will be having more order or less randomness. You can see less randomness is a better word than disorder, I have told you. Okay, so when you increase the volume, you will see that certainly the molecules can occupy a greater space and there will be more randomness. More randomness means what? There will be more entropy, because entropy is a measure of the molecular randomness. Okay, that is a logical justification for what we have discussed here, because nothing has been mentioned regarding the heat exchange here, but okay, you can see that it's what actually is happening is that the energy utilized for expansion, okay, that will be compensated by the heat supplied by the reservoir. That is what actually is happening, but you can explain the phenomenon in different ways. See that anyway, this is the answer that we have got. Okay, now let's go to the next problem. So second problem. See, the second problem says the heat power transmission through a copper rod, means heat power, okay, heat power. Suppose that okay, a copper rod, some copper rod is used to, this is a copper rod, it is used to transfer power, means energy, in the form of heat, okay, when it is connected between two reservoirs. So you have got two reservoirs at 27 degrees Celsius. One is at 27 degrees Celsius and the other is at 127 degrees Celsius. Okay, 127 degrees Celsius. So means I can say this is 127 degrees Celsius, and we say, because already I have put up the arrow here. Okay, and the other one is 27 degrees Celsius, right, is 10 watts. So power is equal to, it's given us 10 watts. 10 watts means 10 joule per second, right? 10 joules per second. So in every second 10 joule of heat is transferred. That's all the meaning, right? So what do you have to calculate? We have to calculate the rate of entropy production. Why the word rate here? Rate of entropy production, because here rate of transfer heat is given, so you are asked to find out the rate of entropy production. Doesn't matter, you take it for second per second, that's all. Okay, so what we'll be doing is here, see one thing. First thing is that we have to convert this degree Celsius to Kelvin. So what is 127 degrees Celsius? You add 273, so this is equal to 400 Kelvin. And so what about the 27? That is 300 Kelvin. So you can consider these two are the two reservoirs at two different temperatures. So from 400 Kelvin, the heat flows to 300 Kelvin at the rate of 10 joule in every second, right? So now let's say what will happen here. So this is the first category problem that I have discussed before. So problems involving reservoirs. So one reservoir is losing heat and the other reservoir is gaining the same amount of heat. That's what is happening. Okay, so what will happen? The reservoir which loses heat will be having lesser entropy, or it will be losing entropy, and the other one which gains heat will be gaining entropy. Okay, so let's calculate in such cases the entropy change of each of the reservoirs separately. That's what you have to do. So let's say delta S of the high temperature reservoir. We say that delta S of, let me say that this is I'm naming it as some H and I'm naming this as low, high and low. Okay, delta S for the high temperature reservoir. Okay, high temperature reservoir, what will be equal to? That is equal to the heat transferred by temperature of that reservoir, Q by T. So I may say that Q by TH. Okay, now one thing to be taken care, this Q, what is this Q? This Q is heat that is lost, so I have to put minus. Okay, So that is equal to how much? We are calculating per second, that's all. Okay, that is what? Minus 10 joule per second. So you'll be getting entropy rate of entropy, because it's per second, that's all. Minus 10 by th is equal to what? 400. So that much is equal to minus 0.025 joule per Kelvin. Okay, joule per Kelvin. But since here it's 10 joule, instead of heat, I have actually substituted power, so that will be per second. So what I'm getting is the rate of entropy. So let me put up here second, joule per second per Kelvin. That is the thing. So that's a special case. Now similarly you can find out delta S for the low temperature. So delta S for the low temperature reservoir, that will be equal to what? The low temperature reservoir is gaining heat, so Q amount of heat is just transferred. So there will be plus Q per second by TL, the corresponding. So that will be equal to how much? It's again 10 divided by 300. Okay, so that is equal to 0.033 joule per Kelvin second. Okay, since it is rate of entropy, that's why there is a joule per Kelvin second, right? Therefore what happens? Total rate, you have to find out determine the rate of entropy production. So what is happening here? Therefore net rate of entropy production, net rate of entropy production, what will be that one? Because one is positive and other is what? Negative. So what is the net rate as far as both the reservoirs are concerned? So that will be equal to 0.033, right, minus 0.025. So that's equal to 0.0000833 joule per Kelvin second. So that is the answer. So this is a type of problem involving heat reservoirs and the transfer of certain amount of heat between them. So you can approach the problem like this. Okay, now going to the next. So you can see in the next problem, calculate the change in entropy of the universe. Calculate the change in entropy of the universe. So you are asked to find out that for the universe, if a quantity of 100 kilojoule is transferred from a reservoir at 553 Kelvin to another reservoir at 278 Kelvin, it's of the same type, but only instead of each individual reservoir, they are asked for the universe, and it's also same direct problem that we have done similarly just before. So here what you do, here also you do. So loss of entropy, we can say loss of entropy for the temperature, high temperature reservoir, loss of entropy of, okay, I can say some reservoir, from a reservoir at 553 of R at, you can name if you want, this one is some R1 and other one is some R2 or something like that, at R at 553 Kelvin. Okay, so how do you calculate? That is equal to Q divided by temperature of that reservoir, right? Okay, so I'm naming it as R1. So this one is T1. Okay, so Q by 10. So it is loss of entropy. Okay, so I have to write this one as minus. So that is equal to how much? 100 kilojoules. So it's 100 into 10 raised to 3. Okay, joules per Kelvin. T1 is equal to what? 553 Kelvin. Okay, so joule per Kelvin. So you work out this one, you'll be getting it is minus. Minus is there because it is a loss of entropy by the high temperature reservoir, always minus 180.83 joule per Kelvin. That will be the answer. Similarly, what will happen? Whatever heat is lost by the high temperature reservoir will be gained by the low temperature reservoir. So there is a gain in entropy, gain of entropy of R at how much? 278 Kelvin. Okay, let me call this one as some R2 for the time being. Okay, so that will be equal to, again, the same amount of heat is lost and gained. So it is plus Q divided by temperature of the low temperature reservoir, Q2. We consider that this is the process is internally reversible. So it's equal to how much? 100 into 10 raised to 3 upon 278. So you will work out this one, you will get this one is equal to some plus 359.71 joule per Kelvin. So that's the answer. Now what we are interested, what is the total change in entropy of the universe? So delta S for the universe means, universe here means what? Okay, you can just add all this. Okay, that is a net gain in entropy. Okay, so that is equal to, you add these two, first case and second case, so it will be equal to 359.71 minus 180.83. okay, and you will get this is equal to 178 point something 0.8 joule per Kelvin. And you note one thing, delta S of the universe has turned out to be positive, as we expect, because there is some sort of irreversibilities that actually exist in the during the process. Okay, so delta S is equal to, delta S of the universe is positive in all irreversible processes. So there is some sort of irreversibilities that is actually involved in the process, right? So that is positive as we expect. So now I think we'll do other problems in the next session. Thank you.